Hello, my name is Logan Boswell. I graduated from Texas Tech University with a major in biology and a minor in chemistry. I've been working on this idea out on my own for 7 years now. I am going to try and fail to sum up what I have found in 5 minutes. The purpose of this video is to say, hey, this might be a thing, wouldn't that be cool? If every atom was the same size and shape, then what would it look like? I came up with this model and I call it the atomic pixel. It looks better closer up. An atom can only make a certain number of shapes due to the bonds it makes with surrounding atoms. Here, I show the shape that most elements make when forming bonds. The shape an atom can make depends on the number of electrons it carries, and the number of electrons it carries kind of depends on which element the atom is. Oxidation states complicates this, but at least here you get the general idea that there is a somewhat limited number of shapes an atom can make. The atomic pixel is a geometric object that can make all of those shapes. It is like a rephrasing of VSEPR theory that is a bit more user-friendly. Instead of bonds between atoms being warping orbits of probability waves, here they are just two balls making flat surface-to-surface contact. That's right, my atoms are touching one another. Shown another way, here are those same shapes highlighted inside the ball. As you can see, the vertices correlate with an outward-facing flat surface. The tetrahedron faces I have specially marked since they are the ones used most often. They are kind of like the sweet spot for making bonds. The design of this ball is somewhat simple. Take a 60-sided polygon, extrude it so each side is now a square face, and rotate it 60 times around one axis to form this disco ball-looking thing, where each flat surface is facing directly away from the center of mass. Then make the equator strip of squares 120-sided and make it jointed with the two hemispheres so that it can wiggle just a little. This took me a while to figure out. The angles aren't exactly perfect. For instance, the angle between the tetrahedron faces is 108 here instead of the perfect 109.5. But you know what? It's functional, which is good enough for me. If it's not good enough for you, then make your own atomic model. It's not that hard. Ring structures sometimes diverge from simple tetrahedron. For example, resonance structures, when electrons are delocalized and spread across multiple atoms, those atoms are represented as lying flat on one plane. So that is what I have here. These atoms can be bonded solely by their equatorial faces so that they all lay on the same plane. When the rings are not resonance structures, they make predictable conformations like the chair formation I show here for the 6-membered ring and the endo position of one atom of a 5-membered ring. It kind of behaves like a leaf when it is hydrated versus when it is dehydrated. Smooth and flat when hydrated with electrons, and crinkled up when dehydrated of electrons. Now, with those shapes established, I can show you what a reaction would look like. Carbon is black, hydrogen is red, and oxygen is blue. Here is a simple hydrolysis reaction. H2O comes in, donates a hydrogen atom to the other oxygen, and the remaining hydroxide bonds with the other side to make ethanol. And how cool is it that the name of this software is Fusion, and I'm in here putting a bunch of atoms together. So cool. Of course, it can't just do chemistry. It would also have to agree with crystallography. So I have some examples to touch base with those guys. Crystals are made up of unit cells, which are boxes that can tell all of three-dimensional space. There are 7 different families of unit cells because the boxes that make them up have different angles and lengths. The simplest of them is cubic, and I have diamond for example. All the carbons in diamond make tetrahedrons. All sides of the unit cell are equal, and you can see how the pattern can repeat itself to make a crystal. For the hexagonal family, I have graphite, also carbon, which forms these long overlapping hexagonal sheets. For the trigonal family, I have quartz, made up of silicon in purple and oxygen in pink. That one hippie girl you did in college that surrounds herself with amethyst? This is that. This is her god. For tetragonal family, I have rutile, titanium dioxide. Notice how two sides are equal, but the third is not. For orthorhombic, I have marcasite, iron disulfide. Notice how all side lengths differ. And the sulfur doesn't make an ideal tetrahedron or a triangle, but it does make face-to-face contact. I would have liked to also have examples for monoclinic and triclinic families, but these are less like crystals and more like bowls of soup. Oh my god, just look at that. Who has the time? I am too humble to attempt modeling that at this point in time. Moving on. The first thing anyone would want to build with this model would be the DNA double helix, which I have been trying really hard, y'all. But I'm losing the wrestling match with my 3D modeling software to get the angles just right without the balls colliding when they shouldn't be, and the software from crashing because there's a lot of atoms in there and a lot of data for my toaster to render. So it ain't perfect, but at least you can see the difference between the ball and stick model, the space filling model, and now the atomic pixel model. Don't look at the file name. It's not perfect, but it gets the idea across. Y'all can see what I'm reaching for. A weird example where my ball still works would be Buckminster fullerene, which is 60 carbon atoms bonded together in the shape of a soccer ball. This one took me a minute to puzzle out. These carbons don't make a perfect tetrahedron, but the bonding angles required to form this monstrosity are contained within my ball, so that each of these balls are making flat surface-to-surface contact. My original intent was to design and patent a toy ball that mimics an atom, and then kids and adults alike can put them together like Legos to make molecules and simulate reactions. But you can't patent an abstract idea, which is about as far as I can carry this idea. So my thinking is, make a video, show the world this pattern that I see, maybe something will come of it, maybe not. I'm still working on this, very slowly, because I have to work for a living, but at least y'all can see that there is something over here.